Hello, everybody. Thank you for staying late. My talk will be around 15 minutes, so we'll be probably right 5 minutes on the happy hour. So I'm really delighted to be here presenting on video compression efficiency for live encoders. Let me briefly introduce myself. I am Ramzi Hasib. I'm a principal software engineer with AWS Elemental. I'm part of the Elemental video engine team. My team focuses on the decoding, processing, encoding library that powers AWS Elemental transcoding products. Like I said, for the next 15 minutes, I'll be talking about techniques to optimize compression efficiency for live encoders. I'll finish with some results and conclusion withdrawn from this work. So throughout the day, we've been talking about quality, talking about improving efficiency, improving compression efficiency. So there are four major techniques that emerge throughout the years. The first one is the novel coding tools, or like the new intra, or the new transform schemes, or the new quantization. The second one is optimizing these coding tools, how to use these tools to better bid rate. The third one is when you have specific scenarios optimization, like the cap VBR, elemental QVBR, per title encoding. And the last one is, in the case of presence of noise, you probably will be using an input pre-filter to reduce complexity and reduce file size. Obviously, the novel coding tools continue to drive a new generation of codec, but this becoming with the diminishing returns, especially it's challenging because you need a new decoder specification, you need a new decoder implementation, which is non-trivial for decoder hardware implementation. And obviously, there is always the compute cost for these new tools. Compression efficiency in live encoders is really challenging. So you have the aspect of real-time processing. So you have to meet the timing, you have to meet the tight timing constraints. Not only that, you have limited compute power that comes with limited latency and high throughput for resolution like the 4K. So compression efficiency in live encoder is still being researched and developed in our industry. So one of the techniques we used in Elemental is to improve compression efficiency is the real-time machine learning-driven dynamic encoder configuration. It's a long name, but the explanation will be easy. So typically, a video encoder comes with the configurable command lines option. And these command line options, you can select one among many. And these will optimize your quality or optimize your file size. And obviously, they have varying impact on efficiency. Let's take the example of adaptive quantization. You can select the range from off to maximum. Again, you have around 20 options to configure for each typical encoder. And these options are really highly content dependent. So they will target specific or fix specific problems with the video. So combining these two, the search space is astronomical if you want to take it from an optimization perspective. So video codec engineers came up with the solution of presets encoding recipes or quality recipes. So what are these recipes or presets? So the objective is to simplify the encoder optimization. So you use a predefined set of configuration options that you have a highly expertise put into these presets, and that target specific case. So we can define film grain presets, or screen content presets, or sports presets. Presentation in mile-high video without Big Buck Bunny is not a successful presentation, so this is the Big Buck Bunny. So let's take a content or video asset, live video assets, composed of 4 distinct sequences. Because it's a live content, so the user or operator could pick the film grain tuning. And if that film grain tuning is used along the video asset, what happens is the quality on the first content will be optimal. But obviously on a screen content, a film grain tuning will lead to visible artifact and non-optimal video quality. So it is clear that using these presets, the way they're designed, is not optimal. For various reasons, the biggest reason, I think, is the limited granularity. You can apply them only on the sequence level. They require a high level of expertise. And there is a lot of manual tuning. So there is no auto way of doing that. Again, content adaptive encoder is not new. It's been around, I think, since 2016, 2017, something like that. And it was targeting mainly rate control, like the adaptive bit rate. And it worked only on video on-demand application. So there is clear need for dynamic content adaptivity in live applications. So what does this feature offer? This feature offers finer granularity on encoder settings. We go down from a sequence level, down to the GOP level, down to the frame level, and even to the macro block level, even to the DCT coefficient. So what we're offering is a content adaptive with finer granularity. And obviously, we added another dimension to this, which is the compression and rate control awareness. Why is that? Is because artifacts or sensitivity to artifacts is different when you have coarse quantization. Like for low bit rate, you can tolerate some blurriness, but that's not the case for high bit rate. So we added this dimension as well. Back to the Big Buck Bunny and the same video asset. So what we're proposing is, instead of using static presets throughout the entire video asset, we're adapting the encoder configuration for each sequence separately. And actually, we go even further. We adapt on the GOP level, frame level, and block level. So as a design principle for this feature, obviously has to optimize video quality, has to be dynamically adaptive to content, and of course, high throughput and low latency for live application. And obviously, it has to be scalable and robust. So how did we design this feature? At the heart of this feature, there are 2 modules. The first module is the content analysis, where you have a look ahead of frames, and you extract features from these frames. And these features are used by the prediction module. The prediction module is an ML-driven module that predicts the GOP frame block level settings. A quick talk on the machine learning and what we used as a model. So what we used as a model, we used a meta-ensemble. And the idea of meta-ensemble is perception is, there is no one dimension to perception. So there is the artifact, you have multiple artifacts, and you have objective metrics that measures those artifacts. So what we decided to do is each artifact or each aspect of vision is modeled by a certain objective metric. And at the end, we stack these predictions and generate the optimal prediction using a voting system that uses learned averages. While the first technique focuses on configuring the encoder, we went even further, and we found out that the input pixels themselves, they need some optimization. How is that done? So the idea to pre-filter the video prior to encoding is not novel again, and was mainly used in the presence of noise. and led to visually appealing results, reduced size, and it solved the problem in the case of noise. The advantage of these filters are the following. So the biggest advantage is these filters are codec agnostic. You can use them on MPEG-2, AVC, AV2, AV3 in the future. So as long as you have input pixels, these filters will work. And the second advantage is there is no decoder spec needed, so a change needed. So you can keep your decoder as it is. The third one is there is significant efficiency increase. And obviously, in the presence of noise, for instance, it leads to visually appealing results. Again, the idea of input filter is not new. It was proposed in VP8, VP9, and still, even in AV2, is still being part of the AV2 efforts. At the heart of these filters is the pixel domain filters. The idea of pixel domain filter is it's a weighted average between current block P and the candidate block Q0 and Q1. And using a bilateral weighting function like the bilateral filter or the non-local mean, you come up with the filter block. As an illustration, the HM temporal filter weights the current pixels with the motion compensated pixels using the bilateral weighting function and adding some QP scaling. The LIP AOM AV1 temporal filter follows the same principles with a small modification like the use of the non-local mean filter being block-based and adding adaptivity to noise level. While these filters delivered on the efficiency in noise content, we found out that these filters are not recommended for pristine content, as these filters will cause non-optimal filtering. The manifestation of this is visible sharpness loss, visible blocking, especially when motion estimation fails, like occlusion or fade or something like that. And there is also blurriness in texture and film grain. Transform domain filter are another alternative for filtering. BM3D, as an example, continue to be one of the state-of-the-art filters, even in the deep learning era. The advantage of the transform domain filters is you can filter certain bands of frequency. So they offer a higher adaptivity, or actually they offer higher fidelity to the sequence. So you can select the areas or the bands of frequency for higher fidelity. So comparing the pixel domain and the temporal domain, obviously the pixel domain filters are great in bandwidth reduction, but they come at the cost. They are non-usable for pristine content. Obviously the compute cost. The transform domain filters are better with texture preservation, but they require a lot of hyperparameter tuning. Quick note on the deep learning-based filtering. Obviously, they offer greater filtering capabilities. But for live application, these filters are not usable, at least at this point, because their compute cost is high, their higher latency, and reduced throughput. So combining the discussion of the previous section, so how to design an optimal filter. Obviously, the optimal filter has to be a dual domain filter to benefit from both filters. It has to have some fidelity to the original signal to be used in pristine content, and reduce bandwidth, obviously. So we know that pixel domain filters are great with bandwidth reduction, but they come at the cost of blocking artifacts, sharpness loss. Transform domain filters, on the other hand, are great with texture preservation, but they come, again, at the cost of they're harder to tune. And combining these two filters is an even greater problem. So what we're proposing is a perceptual threshold module. So this module will control the strength of each filter, will compute the perceptual threshold for the transform domain filter, and we can compute the aggregation weights for at the end. Quick note on the perceptual guided thresholds. Classically, in the transform domain, thresholds are constant, which leads to visually non-optimal filtering. What we're proposing an HBS, or dynamically adaptive thresholds, that leads to visually optimal results. Since we talked about a human vision system, and Professor Aaron Bovik mentioned the contrast masking. I have a slide around that. But other models we use in the perceptual thresholding, we use contrast sensitivity, we use luma adaptation, and actually we add a new one, artifacts visibility with the presence of, or with quantization. The contrast sensitivity function is a function that tries to separate in an empirical way the space into visible frequencies and invisible frequencies. And obviously, the invisible frequencies are the frequencies you will filter. Texture masking, like I mentioned, is when you have two blocks that have different texture distribution. On the top, you have a random, busy, complex texture. On the bottom, you have a smooth, clear edges. And when you add noise or any distortion to these blocks, it's obviously clear on the top, the noise is masked, or the distortion is masked. And on the bottom, the noise is pretty clear. And in our design, we found out that an optimal filter has to be quantization-aware filter. What that means is our filter is an in-loop filter that sits next to the main encoding loop. And it's, again, block-based filter. And we did the multi-model. So for each QP level, we have certain filtering thresholds. So to combine the HVS model and the block-based filtering, we come up with the perceptual threshold as a function of human vision system and QPs. To solve the aggregation problem, I think what we did is separate the space into preservation zone and heavy filtering zone, and we used sigmoid scaling to transition between the two zones. Now, let's head to the results. So the content adaptive dynamic encoder configuration is a lightweight feature. It takes less than 2% of an ABC encoder, and this was deployed in live application. On the objective metric side, for a dynamic content, we measured around 7 to 20%, depending how the content changes. And what's important is the subjective comparison. We found that it will get you around 7% in bandwidth reduction. As an illustration, on the left you have, for the same number of bits, this new feature deliver clear quality improvement. The input pre-filter, again, is a lightweight filter. It takes around 18% of an ABC encoder, 13% of an HAVC encoder. On the VMAF improvement, I think we get around 18 to 15, and this is highly content dependent. So if you have more distortion, obviously you will have higher bandwidth reduction. One last note about this filter is this is a high fidelity filtering, so it's a non-destructive filter. So if your content is with film grain, this filter will preserve the film grain. It does not destroy the artistic intent. And it works for a range of pristine to heavily distorted content. So to conclude, we showed that we showed two techniques for improving compression efficiency in live application. That led to substantial compression efficiency. And again, it comes with reduced latency and low compute cost. And that concludes my talk. Thank you, folks, for staying. Actually, I have a joke before we had to. I had to. Didn't mean to do that. So I asked ChatGPT to give me some jokes about video compression, and it did not work, so I wrote my own joke. You have to laugh. So the question is, what did the video encoder say to the pixel after a long day, like today? Let's call it a night and decompress. Let's call it a night and decompress.